I mean, he emailed this morning,
He had a rough.
but on something that else. He had a rough trip?
He had a rough trip, is what he texted me when I asked him that, do you make it or not? He made it last evening, so.
So he did make it eventually. Okay. All right, shall we?
We are ready whenever you are.
Yeah? Okay. Well, welcome everyone. It's my great pleasure to introduce Madie Mamer from Georgia Tech today. And a little bit of background here. Madie is originally from the desert in Southern California. Did her undergrad at UW, the other UW, the lesser UW. And is now a PhD student with Alex Robel at Georgia Tech. And you know, it's a small world, and at some point we realized that Nicolas, who's a grad student in my group, studies how waves erode ice cliffs, and then I don't know how we came to this realization, but Madie also studies how waves erode ice cliffs. So we realized we should probably talk to each other and use this as an excuse to establish a collaboration. And Nicolas was so worried about this overlap that he literally went to Japan yesterday to avoid this. No, he went to Japan for other reasons, but he's not here. Anyways, ice, oceans, there's nothing better in the world, so I'm very happy to introduce you, and please take it from here.
Yeah, so thank you for the introduction, and everyone I've met so far, you've all been very kind, so I'm looking forward to meeting more. Today I'm going to talk about two projects from my dissertation research. They are ice-ocean interactions at various scales and various regimes. I was a bit ambitious in trying to stuff two projects into this presentation, so I apologize if I go over things very quickly. But please interrupt at any point if you have questions. I'm going to attempt to leave about 10 minutes or so of time at the end for questions. Great, so let's get into it. So why do we care about ice sheets, and why do we care about how they're melting? Well, we know that our ice sheets are losing mass. Here we have observations from satellites of Greenland mass loss, and we see that a majority of it is concentrated along the coast and in the south. And it's a similar story for Antarctica, where we see a majority of mass loss concentrated in this West Antarctic area around the Munson Sea embayment. This is really critical to understand, not only because the ice sheets themselves are important, but because of what they do for our climate. So our ice sheets, as they melt, are going to contribute to sea level rise. What I showed here are multiple figures from a series of both observations and models. The observations are in dotted, and the colored lines are models. And we're seeing the different components of sea level rise over the last 20 or so years. And while a majority of the sea level rise that we have witnessed so far has been driven by thermal expansion, which is that flat E there, what we are likely to see in the future is more mass loss and sea level rise being driven by our large ice sheets. So it's important to understand how they're losing their mass, at what rate they're losing their mass, and what that might look like in the future 100 or 200 years from now. What is also interesting about how they're losing their mass is that a majority of it is concentrated along the coast, like I showed in those first two images. And if you're unfamiliar with ice sheets, their marine terminating portion, or their ice shelves, are really important to ice dynamics. So we have these large ice shelves that provide a sense of buttressing, or backward force, on the grounded ice. And if we lose that portion of the ice shelf, then we're going to see acceleration of the grounded ice and thinning. I really like this figure from a 2016 paper looking at the so-called safety bands of Antarctica, which are essentially the regions of ice shelves that we could lose and not lose any of this buttressing power. But as soon as we start going beyond that red line and into the green zone, then we might see a reduction in buttressing and acceleration of ice, grounded ice flow of thinning. What's also interesting is in the last decade or two, we've started realizing that a majority of mass loss for our ice shelves in Antarctica are driven by basal melting. So what we have here is a figure from a 2013 paper looking at basal melt across all the ice shelves from a satellite-derived product. And then in our pie charts, we have the representation of mass loss from calving, which is the dashed portion, and from basal melting, which is the dark black portion. And what is shown is that throughout all of Antarctica, a majority of the mass loss is driven by basal melting, and it accounts for a substantial amount. So it's really important to understand how the ocean forces mass loss of ice shelves. And a more recent observation of mass loss around Antarctica from Sushila Dusamili's thesis in 2020 shows that our melting around Antarctica is heterogeneous, both in time and in space. And so this makes it really difficult to parameterize. And it's also very difficult to observe. We really only have a handful of observations within ice shelf cavities and near ice shelf terminus fronts and within melange and sea ice because it's a difficult environment to get to and observe. All of this adds up to high uncertainty in how we model ice shelves. So what I'm showing here is a plot that shows this uncertainty from a model intercomparison project published last year, where on the top panel we're looking at surface mass balance. Each color represents a different model. And on the bottom panel we're looking at ice shelf melt. And what we see is that we get a lot larger spread and a lot more intramodel disagreement for ice shelf basal melting. And it accounts for most of the uncertainty in how we model our ice shelves and ice sheets' contribution to sea level rise. What's also really interesting about this regime is you have multiple dynamics happening at multiple spatial and temporal scales. So I really like this figure from a review that came out actually this year in January that shows what an Antarctic idealized ice shelf system might look like, where you have circumpolar deep water flowing into the continental shelf. It might engage with the ice shelf and become modified water. There's kelving, there's sea ice, there's deep water formation, there's polynyas. It's a highly dynamic system. And what we are attempting to model in this system when we're modeling basal melt is the transfer of heat across a very thin boundary layer, which is represented there in figure B, which is order of centimeters to meters. So really the question is, how do we capture all of these scales in order to model that cavity-wide circulation? So this is a figure from that same review paper that shows all the different fluid processes that happen across the range of length and time scales, going from turbulence convection all the way to cavity-wide circulation. And what I'm going to talk to you about today and where my interest really lies is in kind of the middle member of this review, where we have plumes and subglacial discharge, and we have our warm salty water interacting with the subglacial hydrology, and maybe we have waves acting against icebergs. And that might happen on the scale of meters to kilometers and on the time scale of minutes to days. So moving into my work and what I do, I'm going to talk to you about two projects today that make up the first two chapters of my dissertation. The one focusing on seawater intrusion near grounding zones and grounding zone hydrology. And then the second is the one that Till briefly mentioned, thinking about ice erosion by waves. Alrighty, so crash course on grounding zones. Grounding zones or a grounding line is where an ice shelf goes afloat for the very first time. So you can kind of think of everything upstream of this part as being grounded ice, and the grounding point is that transition to where it becomes an ice shelf when we get this floating portion. Now traditionally when we model this in both a standalone ice sheet model as well as a couplet model, we don't allow for interactions between the subglacial hydrologic system and the open ocean system, except for maybe the impact of freshwater plumes, which I have graphically displayed there. Now the subglacial hydrologic system contains all of the fresh glacial melt that may be melted on top of the ice sheet or it melted at the base and flowed to the grounding line where it ejects as this buoyant plume. This can be a disconnected network or kind of a lateral spread, or it can be highly channelized in an efficient manner. What's interesting is recent observations have described this as a very dynamic, hydrologically active place and not just a static hydraulic barrier like we represented in models currently. Here I'm showing some of those observations that motivate this idea. This here is imagery from a satellite looking at the CAM ice stream, where the white line depicts the grounding line, and then this gray image, you can see this sort of channel-like structure crossing over the grounding line. And they hypothesized that this subglacial water conduit might provide an opportunity for seawater to come upstream of this grounding line. So you can think of the ocean being here and the grounded ice being here, and the seawater can maybe come in upwards of 6 kilometers across the grounding line. Another way of thinking about this is that we have tidal modulation of grounding lines. So the grounding line isn't static in time, but it actually moves on tidal cycles. And that's what that top figure A shows on the right-hand side, where the blue scatter points represent grounding points at low tide, and the red scatter points represent grounding points at high tide. The other lines on those figures have been other identified grounding line points from other methods. But what this paper identified is that you can have this grounding zone width that is order of kilometers. And we currently don't accurately capture that in models at all. And we only limit our ocean force melting to the ice shelf cavity itself. There's been some other satellite observations that I show here on the bottom side of that right hand. That's looking at INSAR, where they can identify in those red lines there different areas of grounding lines across different tidal frequencies. And what they've discovered is that this seawater during regions of high tide, so the ice sheet is, or the ice shelf is being moved up and the grounding line's moving inland, that seawater can intrude and get trapped in bathymetric lows. And that's what they had outlined in the green and the yellow, green and the orange circles there in panel A. And then B and C is showing the direct INSAR products where you see these fringes, which is indicative of water being there, versus the tie-dye-like regions are showing grounded ice. There's also been some recent theory work on this idea over the last 5 or so years. This panel on the left side is thinking of, okay, what if we were to construct a really simple model where we have 2 layers of buoyant water of subglacial discharge and a salt water coming in? What are the dynamics that set the intrusion distance? And then if we take that intrusion distance and apply a melt rate that decays to 0 at that inland point, what happens to ice sheet melting? And so that's what they did with ISSM, where they took the grounding line melt rate, decayed it to 0 into this intrusion distance, and what they see is that your mass loss greatly increases because you're extending the regime of ocean-induced forcing. And this was definitely like an idealized model, but it motivates this idea this regime might be important for modeling how the ocean forces ice sheets to respond. A paper last year went a little bit further on that theory route and also said, okay, well, if the seawater intrusion is coming in and it's melting ice, then the ice itself is going to respond, it's going to melt away, and it's going to increase the size of that cavity. And what they found is that you can get an unbounded intrusion in some regimes of fruit gumboras. So this motivates my research and kind of sets up 2 nice questions that I'll walk through today. Is what controls the length of seawater intrusion? So if we say that this is real and this exists, then what are the key parameters that set the intrusion distance? And then secondly, does turbulent mixing influence the intrusion distance? And this second question is a result of my advisor's theory work and all the reviewers saying, well, turbulent mixing is going to erode away the intrusion and it's going to completely get rid of it. So we wanted to ask, okay, well, what happens if you allow for turbulence to occur? And then secondly, now that we have these models of this regime, what does the vertical structure of this intrusion look like? And can we leverage that vertical structure to our advantage to understand how we might parameterize this regime in an ice shelf or an ice sheet model? So in this project, we went through a whole slew of parameter spaces to kind of get at what's happening in this domain. For today, I'm only going to go over these 2. So I'm going to look at turbulent mixing and the freshwater flux or the subglacial discharge velocity. And how I'm going to do this is by using a high-fidelity computational fluid dynamics solver, ANSYS Fluid, which solves the Reynolds average Navier-Stokes equation, and then we also turn on a turbulence equation to describe the turbulent mixing. And so we have a really simplified domain where we have some subglacial environment that has a subglacial discharge velocity, UF, on that right side there, interacting with this ocean basin that has some seawater velocity coming in on this side. The ice is graphically displayed there, but we don't model the ice. However, we do enforce a boundary condition on the top part of the subglacial environment to mimic the liquidus point that is normally used when modeling the interface. And then we prescribe a 0 gradient flux at the out boundary to conserve mass. Now, before talking about turbulent mixing and freshwater flux, I'm going to walk through some figures to show you what the results look like and what we're interested in. So if we do like a standard case where we have a run-of-the-mill freshwater velocity and normal medium turbulent mixing, and then take a depth average density profile throughout the subglacial environment, that's what this is showing. So Our x-axis is our distance along the subglacial space, 0 being the grounding line. Further up is into the subglacial environment, and then our y-axis is our density. And so we see we get this like nice wedge of intrusion of about 5 meters in this space. And I will say the scaling between the results presented here and the results identified from the observations and the theory work are different, and that's because of the drag coefficient. So I'm not going to delve into that, but if anyone has questions, I'm happy to chat about that afterwards. We can also look at vertical slices throughout our subglacial domain. So here on the y-axis, we have our distance from the ice, where 0 is closer to the ice and -5 is at the base of the subglacial environment. Darker lines are closer to the grounding line, and lighter lines are into the subglacial environment. So what we see is that we get colder water as we move into the subglacial space. We get fresher water, and then within these kind of intrusion regime, this salt wedge forms, where we get this two-layer exchange flow. And so this is really interesting because we get this nice wedge of seawater intruding in that decays back to a classic uniform pipe flow with subglacial environment characteristics. Okay, so this is our standard case that we're going to compare everything to as we move through the turbulent mixing regime and the freshwater flux regime. So to model turbulent mixing, what we do is enable the KE2 equation turbulence closure model. And without getting into turbulence modeling too deep, what essentially this is saying is that our eddy viscosity, mu t, is some function of our turbulent kinetic energy, our K squared, divided by our dissipation. And those two are related to each other by this cofactor C mu. Now C mu has empirically been found to be about 0.09. However, it can vary depending on what fluid regime you are. So we use that to our advantage to simulate either more or less turbulent mixing. And we range it over 3 values, a high, a medium, and a low turbulent mixing case. So what I'm showing here is that same plot that I showed the first time, but there's an additional line on it, which might be hard to see, because for the high turbulent mixing case, we get almost an identical intrusion distance. And for the low turbulent mixing case, the same is true. And just to really send this message home, we also ran a laminar flow case, right? So we have no turbulent mixing whatsoever. And what we see is that turbulent mixing has almost no effect in this regime of intrusion. So it doesn't get rid of the intrusion persists. And this is really because what we're modeling here has a very low Reynolds number. So it has a very low turbulent viscosity. And that means that turbulence is going to play no role. And if we take our domain to be representative of what we might expect in Antarctic-like conditions, what this is saying is turbulence doesn't have a play, and we can let our seawater intrude to some distance. Alrighty, so now what we looked through is our freshwater flux. So what I'm varying here is the speed at which our freshwater is discharging into this environment, and we range it over 3 likely values. We don't do anything higher than 5 centimeters per second because what was found in some of the original theory work is that if your subglacial discharge velocity has a critical fruit number, so if it's above 1, then seawater can intrude. And so this is kind of the highest we can go without completely getting rid of our intrusion. So again, this is the similar depth average density transects. There's a lot more lines on here that I'm not going to go through today, but if you have questions, I'd be happy to chat more about them. The blue lines and the green line are exactly what I showed before. And what we see, right, is that if we have a freshwater speed of about 0.5 centimeter per second, then we get about 5 meters of intrusion. If we increase our freshwater velocity by magnitude, then our intrusion distance decreases by about magnitude. So instead of 5 meters, we have about 0.5 meters of intrusion. And conversely, if we decrease our freshwater velocity, then we see a dramatic increase in our intrusion distance. So now our intrusion is going to around 25 meters. And so what this means is that our intrusion distance is highly dependent on our freshwater velocity. So it's highly dependent on the fruit number of our subglacial discharge, which has been identified in previous theory. So it's nice that in this high fidelity, more complicated model that we're seeing this to be true. And then I think what's maybe a bit more interesting in thinking about how we might parameterize this regime in a coupled model or an ice sheet model is that the strength of your subglacial discharge not only sets the intrusion distance, but it also sets the mixing dynamics within this regime. So here we're looking at those vertical profiles again. The darker colors are profiles near the grounding line, and the lighter colors are as you move upstream into the subglacial space. This top row is our highest freshwater velocity, and the bottom row is our lowest. What we see for the highest freshwater velocity is we have a really strong thermocline and halocline, and we have this strong exchange flow forming where you have a lot of velocity or a lot of flux out into the ocean and not so much coming in from the ocean. And for our lowest freshwater velocity, we have more uniform conditions in our salinity and temperature profiles, and you get this much weaker exchange flow. So what we see is that our stratification and our exchange flow strengthens with increased freshwater flux. And what's interesting about this is that it is very similar to how estuaries behave, and that estuaries are sent by the river discharge rate in terms of their strength of stratification and their strength of this like exchange flow that forms between the two layers. And so there's this kind of interesting idea of like, can we just treat this like an estuary underneath an ice sheet? And can we borrow from those physics that have been well constrained and well observed to apply to this regime? I think there's a lot of exploration that could be done there. We obviously have very few observations to constrain this, and it would be difficult to include in a model because the scaling would be difficult as on the grid sizes needed to model whole ice shelves. What's nice about these simulations is that they're pretty consistent with observations that we have from a laboratory experiment as well as theory. So here the gray scatter points are from laboratory observations where they had a similar domain of a tank connected to a pipe, and they allowed fresh water to eject through that pipe into the salty tank. And then the dashed line is from the shallow water two-layer theory. And the red and blue dots are from the modeled equations here. And we see some nice agreement between them, so they're consistent. All right, so before moving on to my next project, to just summarize what I've talked through here today, is that we see that turbulent mixing has little to no influence on intrusion distance or structure in this flow regime. I didn't show this, but I have it in here if anyone's interested, is that if we were to look at vertical slices of velocity and temperature and salinity for each of the different regimes of turbulence, we would see almost identical structures. Really what's important is the freshwater flux, right? And so that can be either set by your geometry or the speed of your discharge. And what we see is this influences intrusion distance as well as the vertical structure. And that vertical structure is important because it dictates how the warm salty water is going to get to the ice face to cause melting. If it's strongly stratified, then that's going to be more difficult to mix and more difficult to get that heat to the ice. But if it's less stratified, then you have more available heat to melt the ice. Some other impacts that we have looked into and are considering currently are what happens when the intrusion causes melt there locally, and that puts fresh water into this domain. What happens when the ice shelf melts away and there's a geometric feedback, or maybe you have a really bumpy, porous ground, or maybe it's retrograde. Tides can also be a huge thing, so like I mentioned at the beginning of this project, tides modulate the grounding line and therefore modulate the area exposed to the ocean. And so including that in this regime is really important. And then also thinking about seasonally varying discharge. So if you have an efficient system that has a channelized discharge conduit that ejects water out in the summer, but then is there in the winter that isn't injecting fresh water, then that might provide an opportunity for seawater to come in preferentially at that location, which is one of the motivating figures that I showed at the beginning. So there's a lot of work to be done on this topic for sure, and I think a lot of folks are excited about this idea and how we might include it in models, and I think people are starting to believe that it could be important. Since it happens at the grounding zone, and the grounding zone is a really crucial part of ice dynamics, it's really important that we get that area right in terms of how we're representing melting. And I think this is one way forward of how we might connect the subglacial system to the ocean system and, you know, allow it to be a continuum of fluids and not necessarily a harsh break-off. All right, so now I'd like to transition into my second project, which will be fun to talk to in front of Till, since he has all the great papers about this, and it's really awesome to be here and be able to collaborate with him. So my second project moves away from the grounding line at 1,000 meters depth and moves to some arbitrary vertical ice front. So this could be the edge of an ice shelf terminus like Nicola looked at, or it could be some iceberg, which has been the more traditional way of thinking about this mechanism. And the idea is that you have surface waves on the ocean that propagate towards the ice, and it preferentially carves out this notch at the waterline. The way that we have been thinking about it for the last 40 or so years is that the waves create this orbital velocity, right? This orbital particle velocity. And from that, we can deduce a velocity near the ice front, and we can deduce a skin friction, and through some math that I'll walk through in a moment, get to a melt rate. What's also interesting is that this orbital motion might also be interacting with a background current, and it might be interacting with some natural convective-driven melting from ambient plumes. And then, of course, you might have some stratification in temperature and salinity. I also like this GIF as an opportunity to shout out Till's coining of the name footloose. So, like I was mentioning, you have these waves that erode the notch at the ice, and what's important is that it destabilizes the ice column, so it allows for calving of this upper part, and then that can lead to buoyant stresses at the bottom, which leads to this foot-like structure that might also cause crevassing and further breakage of the ice. And so this is kind of the idea of how it might work for an ice shelf terminus, where it might create high-frequency, low-volume calving events. What's also interesting about this topic of ocean-induced ice loss is that it has a really kind of rich history, or interesting history, like if you look back at it. So the first observed, to my knowledge, the first observed wave notches were by Joesberger in 1978 in the Labrador Sea, where he has these pictures that point out these notches in these overturned icebergs. And he deduced that these were potentially from preferential melting at the waterline, potentially due to waves. And I also like to shout out this picture, not only because it shows all of these really interesting like terrace notches, is it also shows like the dramatic size of icebergs. Because I think a recent appreciation that I've had is that icebergs genuinely can be ginormous, and they account for a huge amount of fresh water entering the ocean, and so it's important to know how they break up and move throughout the ocean, so that way we understand the freshwater flux into the ocean. So this is off the coast of Greenland, and what we're seeing here is potentially multiple notches carved out by waves, and we see them nicely because the iceberg's moving up in time as it melts and it rises due to buoyancy. And it's just massive. And it's really important to understand how these icebergs are deteriorating, because based on 3 different mechanisms of how we might model iceberg trajectories, there can be a huge difference. So this figure here in A is showing if we have a Gladstone distribution, which is like a power law distribution with some amendments to it. And then B and C are both power law distributions of icebergs, both with breakup and without breakup of the iceberg. So if we allow it, instead of just melting away, if we allow it to break up into multiple parts. And what we can see is they have different spreads in where the icebergs might go, in this case for Antarctica. And then like my GIF hinted at a few slides ago, is that in recent years, this has been hypothesized that this mechanism might be important for ice shelves. So what I'm showing here on the left-hand side are figures from a paper from 2021 that, using ICESat-2 data across the Ross Ice Shelf terminus, they uncovered these structures that they've called rampart moats, where 0 here would be the terminus of the ice shelf, and you have this peak in ice shelf elevation, and further upstream you get this dip. And in this paper, they thought, well, maybe it's the footloose mechanism happening. Maybe we're getting wave erosion at the waterline, destabilizes the ice column, it breaks up. You get this buoyant foot, and then that causes a rampart to form, and then due to ice dynamics, you get this moat. And that's exactly what Nicolaus and Till's paper is about, is looking at this system, looking at this effect a bit more in detail, and not only did they see the structure form and then break off over time, but they also used a bending theory to fit a nice curve to the observed curve that we see here to show that this footloose mechanism might be responsible for some of these observed structures. Okay. So hopefully I've convinced you that this is an important mechanism, that it's worthwhile research. Now what I'm going to try to do is explain how remodeling it might be inappropriate, and we can maybe do it in a better way. So like I was mentioning, the history of how we think about this wave erosion feature is quite interesting. So here I show a series of equations spanning 25 years or so. So the first equation here is from a military report from the 1980s, in which, using a theory that's called a Reynolds analogy, which I'm going to go through in the next couple slides, the authors deduce this linear relationship with temperature that describes the waterline melt rate. And when I say waterline melt rate, it's the maximum melt rate that we would expect at that waterline notch. So they said that that maximum melt rate is linearly related to the water temperature, TW, and then some variables of our surface waves, so maybe the height, which is represented by h there, and the period t, and then a characteristic Reynolds number. After about 20 years, 17 years since that report was made available, an amendment got made where we said, okay, well, the melt rate is a function of our waves, and so let's just say that's the sea state, which is the Beaufort scale. And so in 1997, Big came out with a paper where we said, okay, our melt rate is equal to half the sea state, which is represented by our Beaufort scale. A couple of years after that, Big wrote a paper with potentially a student, Gladstone, where they were like, okay, well, we need some dependency on not only sea state, right, the roughness of our ocean, but also on temperature. So they added back in this linear dependency on temperature, T, some cofactor 1/6. They added 2 to it and called it a day. And then a number of years after that, they modified that to become this equation that not only includes sea state, or the roughness of our ocean, but also our ice concentration, which is represented there by I, and then a linear relationship with temperature to some thermal forcing. And to my knowledge, this is what is traditionally used to represent this melting mechanism when we're thinking about iceberg decay. There has been some amendments to the sea state, and maybe not just using like a constant value, which is what the Beaufort scale is, but to maybe include the speed of the wave at the ocean, so using the product of or speed of the wind on the ocean, so using the product of the wind velocity direction at the surface. What is missing from these models is that there is a depth dependency on wave dynamics. So our wave velocity, or the orbital velocity that I showed at the beginning, doesn't act uniformly over depth. And then secondly, that when you melt ice, it's going to put fresh cold water into the ocean, and that might create a meltwater feedback. Now, the second point is really the main motivation that me and my advisor had, of like, okay, you're melting an iceberg, it's going to insulate itself. And there has been some observations showing that water does get significantly cooler, or noticeably cooler and fresher near icebergs. So our plan of attacking this question is to revisit the theoretical estimates and connect it to a quote-unquote ocean domain. And I say quote-unquote because it is very much a simplified box model that we're doing that just has some simplified plume fluxes and background fluxes in. So this is a picture here of that 1980 report that kind of started it all on how we think about wave erosion. And in this report, the main author, Frank White, goes through a derivation called a Reynolds analogy. And the Reynolds analogy essentially relates heat transport and momentum transport to each other. So his argument is that we know something about the wave. We get this orbital velocity as a function of wave properties. Therefore, we might know the friction at the wall and therefore we know the momentum transport at the wall. And in this case, the wall is our vertical ice block, arbitrary ice block over there. And the Reynolds analogy is saying, okay, we know that stuff, therefore we can know our heat transfer because of this. And this really comes down to the log law of the wall, if anyone's familiar with that. So if you are familiar, then the block equation there might ring a bell, which basically says some non-dimensional distance is equal to a slope 1 over k, and then your log of your boundary layer thickness, which is represented by that delta, plus some constant b. And what's deduced out of the Reynolds analogy is we can get a similar law for a thermal log law of the wall, which is some non-dimensionalized temperature equal to that same slope times the natural log of the thickness of your thermal boundary layer plus some constant that's a function of your Prandtl number, which is a known value for seawater. And following this, if we make the assumption that our momentum boundary layer thickness, our delta T, is the same as our thermal boundary layer difference, then we can subtract these two equations and redimensionalize our temperature and get back to a heat flux. And this assumption that the boundary layer thicknesses are roughly equal to each other are somewhat fair in turbulent conditions, because the idea is that in turbulent conditions, what is transporting heat and momentum is your turbulent viscosity, which should be similar for both of them. So if you assume that and do a bunch of algebra, what you can get to is your heat flux Q divided by a temperature difference in some constants like your heat capacity, your velocity of the water, and your density is equal to some function of your friction factor, your CF, and your Prandtl number, your molecular Prandtl number. We can say that our heat flux is equal to some latent heat times density and a melt rate, which is what's traditionally done. And then our friction factor we can say is some function of our Reynolds number. There is some uncertainty in how we identify this friction factor. For waves, this friction is typically taken from bottom boundary layers, like against the sea floor, not necessarily a vertical wall. And then it also depends on if you're in a laminar or a turbulent regime. But if we take all of this, then we can get our melt rate as a function of known properties. So this is where the melt rate equation that I want to start with from the get-go in my model, and is really the base of my model. Okay, so we've done the depth dependency on our melt rate, and now the second thing that we wanted to think about was what happens with meltwater feedbacks. So what we did with that is create this kind of pseudo-hierarchy of models looking at varying degrees of complexity. So our first model is looking at only the ice, so we only have that melt rate equation. We don't think about the ocean evolving as we put fresh water into it. The second degree of complexity is we say, okay, we have this melting, it goes into the ocean cools and freshens, and exchanges with some bar field, some U background. The third complexity is, okay, we have this boundary box, it's getting meltwater, that might create an ambient plume that's going to rise because it's buoyant, and it's going to spread at the surface. So these two are essentially the same, except that we have a plume forming in this second box, and that might allow for ambient plume-driven melting. And then our fourth complexity model is thinking about all of that in addition to this intermediate field. And the question with this intermediate field is, can we get at a length scale where we see a freshening and a cooling? So there's been some observations around icebergs that within, I think, a few hundred meters to a kilometer, we can see this like noticeable freshening and cooling, and we want to see if our model can capture that. I think that is still kind of an open question for us of like what exactly is this length scale that we see cooling and freshening. So what I'm going to show you now is figures of, vertical profiles through our domain. So depth here, our pseudo-vertical arbitrary block of ice is about 100 meters of depth. We're looking at temperature, salinity, and melt rate. The gray dashed line is from the Silva 2006 equation, which was that bottom equation I showed in that series of 4, and the dashed line is that first equation, so they're just two other parameterized. And this is a video that will hopefully play. So what we do is we have our melt rate equation, and then we couple it to these equations that describe temperature and heat transport through all those domains, and we numerically integrate it in time. And each of these colors represent different models corresponding to the colors of the boxes on the previous image. So this dark purple line is our highest complexity model, where we have that horizontally resolved domain. The light orange, which you can faintly see at the top, is what happens if we just allow for the ocean to respond. And then that medium purple, which again you kind of see at the top, is ocean responding with some ambient plume. And then the black solid lines that kind of hang out around 1 and 34 pbt are our background conditions. So what's interesting, and kind of already answers our first question, is like, okay, you see this, you see that the model does something, and its steady state is not the prescribed background conditions that we give it, that it goes to another state. But if it's not really greatly reduced in temperature. So we initialize our system with about 1 degree C of temperature, and if we allow it to reach a steady state, we really see our maximum reduction of 1/100th of a degree, barely. Salinity, maybe the effect is a little bit more noticeable, but ultimately when you combine this, it's not affecting the melt rate. And you can see that because we don't see 4 lines over there on the melt rate panel, right? They all collapse onto a neat line. But what is interesting is the melt rate that we're getting with this Reynolds analogy is much lower than the 2 versions of the parameters that I have plotted there. And not only is it lower at the maximum water line, but it tends to 0 near the bottom of our ice, right? And this is because that waves, their velocity, are going to damp at their wave base, which is about half the wavelength. So if you have a 50 meter wavelength wave, then your ice is only going to feel the effects to about 25 meters depth. And I think that's important to capture in this parameterization. Okay. Now, in the next 10 or so minutes, I'm going to go through. So now if we take this as true and we say, okay, it doesn't really matter if you think about ocean dynamics, taking things away, that it doesn't appreciably decrease your temperature or salinity, therefore it doesn't affect your melt rate, I'm going to focus on only one of the models for the next few results. Okay, so here what we're looking at is, again, those vertical profiles of melt rate, but each line here represents a different background temperature. So this is probably obvious, but that for our highest complexity model, so if we include horizontal transport within our model domain, melt rate increases with background, ocean temperature increases. This is somewhat obvious and should be intuitive. And this melt rate increases linearly with a function of temperature, which again makes sense because our melt rate is a linear function of our thermal forcing. So here in the scatter points, I have our surface melt rates that correspond to each of those profiles, so taken at y = 0 for each of our background temperatures, plotted against their meter per day waterline melt rate. And then the stars are from our parameterization, our Silva 2006 parameterization, so the ones that's traditionally used. And so yes, they're both linear in temperature, which makes sense from the melt rate equations. However, their slope is different, and we see that Silva overpredicts this melt rate, especially at low temperatures. And this is likely because they have that +2 factor, if not accurate thermal forcing. We can also think about how this model might behave as we range our wavelength. So here the different lines correspond to different wavelengths. Lighter is less wavelength, darker is longer wavelength. And what we see is that while you increase your wavelength, you decrease the waterline melt rate, but you increase the depth at which the melting penetrates to. And so if we were to look at maybe -80 meters, what we see is for the longer wavelengths, we have more melting at depth. So again, this is that depth dependency that I was talking about that should be captured in our parameterizations. What I'm showing here in these scatter plots are for each of the models, so all 4 levels of complexity, looking at the ratio of our boundary temperature to the background, boundary salinity to the background, and then our modeled melt rate to that Silva 2006 parameterization that I showed earlier. And what we see is that as you increase the wavelength for our highest complexity model, you decrease your background temperature, you decrease your boundary temperature, but again, not by an appreciable amount. We can almost neglect it. But what is interesting is that as you increase wavelength, you increase the agreement between this model and the Silva 2006 model, although it is still very low values. So this is our melt rate over Silva's. We're capturing about 10% of the modeled Silva melt rate versus 5% at low wavelengths. And this is likely connected to the fact that as you decrease your wavelength, you're decreasing the depth at which the ice would feel the waves. Alrighty, and then we can play the same game looking at our wave heights. So each different line here is for different wave heights. As you increase your wave height, you increase melting across the board. You increase the waterline melt rate, you increase the depth at which it penetrates to. And then these are those same plots now, but just shown for this parameter sweep. We see a decrease in temperature and a decrease in salinity. And as you increase wave height, you increase the agreement with the Silva 2006 model. But again, it's still vastly under predicting. We're still at about 15% of what that parameterization would have estimated. I think another interesting question to ask is, how does this regime interact with natural convective driven ambient plumes? So if you have a block of ice in water, no matter what, it's going to melt a bit if there's waves or not. And this is going to form, if you're in the ocean, this is going to form ambient plumes because the fresh water will be more buoyant than the salt water. And so you get this convective driven melting where you have an ambient plume rising along the ice that's transporting and entraining heat and salt. Now traditionally in our models of iceberg decay, you have your erosion term plus some convective driven term. And so that's what I kind of have here displayed. So our melt rate m dot is equal to that Reynolds analogy that I showed, plus some melt from our ambient plume, which we have our heat capacity Cp, we have our latent heat, and then that gamma T is a turbulent transfer coefficient, which just represents the transfer of heat across a boundary layer. And we can look at their respective contributions of melt in this domain. So again, our ice is about like 100 meters in depth. We're looking at temperature, salinity, and melt rate. The solid lines here are for our model where only wave erosion is allowed. So what we see, right, is that our melting of wave erosion is strongest near the top, and therefore its effect on salinity and temperature is strongest near the surface. Versus the dashed line is if we run our model with only that ambient melting or ambient plume term. And that's the dashed lines. And what we see is that the melting for our ambient plume terms is uniform mostly in depth, and that's mainly because that gamma T is constant in depth for now. In reality, it should change as a function of plume velocity. So that's a small limitation right now. But what also is appreciable is we see a great reduction in temperature and salinity. So now instead of only our temperature being reduced by about maybe 1 or 2%, we see our temperature being reduced by maybe 5 or 4% at depth. And then that decreases as you move up in the ambient plume regime. And what I want to illustrate with this figure is just that, again, there's a lot of complicated dynamics happening here. And it's hard to really disentangle these two in real life. And it's not exactly clear if we can just sum up these two values and if they are acting independently of each other or if they're contributing to one another. And what's also kind of interesting is that our waves, they're an oscillatory thing. And so they're creating an oscillatory boundary layer near the ice, which isn't just a run-of-the-mill normal flat plate boundary layer, which is what we derive a lot of our heat transfer from. So to conclude on this session of my talk, key takeaways. We need to include depth dependency on our wave erosion melt rate. It's really critical to getting this regime correctly and not overestimating melt rate. Our wave-induced changes of temperature and salinity, so if we isolate the meltwater that comes from wave erosion and the effect that it has on temperature and salinity, they're negligible compared to plume effects, and then it's really our plume dynamics, our ambient plume dynamics, that are setting this depression of temperature and salinity near the ice. And then the third one, which I didn't get a chance to talk to today, but what's really nice is, well, I guess I won't go back. What's really nice is for one of our lowest complexity models, there exists a really simple analytical solution that could potentially capture this regime more accurately and would be relatively straightforward to include in existing models. That's really promising. I'm excited to chat with Till about more. And then I alluded to some present challenges and added complexities. Namely, there's no observations really to compare to. So luckily, we have some laboratory experiments being conducted here, which will hopefully help us constrain how we model this. But in situ measurements are basically non-existent, and that's because it's really hard to get up and close and personal with an iceberg or an ice shelf terminus. And also, just if you're there, you're not only measuring wave erosion, but you're also measuring this ambient erosion. You're also measuring surface mass balance, and there's multiple things that go into play. The ocean has nonlinear waves, so it has weird things going on with its wave dynamics. It might not be appropriate to model this using linear wave dynamics. So that we have to kind of understand as well. And this oscillatory boundary layer, like I mentioned, that the wave itself is an oscillatory thing acting against the boundary, and that's going to create interesting boundary layer dynamics. We also have Ekman transport. If your iceberg is large enough, or if it's an ice shelf, then you can potentially have iceberg or Ekman transport around the iceberg itself, and that's going to lend to a whole other regime of fluid dynamics. And then the fourth thing, which I don't have in this model, is your icebergs move. So if we wanted to apply this to an iceberg, we'd have to think about relative velocities around it. Okay, great on time. So sum up the two projects. The first one that I talked about, thinking about seawater intrusion at the grounding zone, what we see is a highly stratified estuary-like system that, because it's akin to estuaries, we can hopefully leverage our knowledge about those systems in parameterizing this regime to understand how the ocean affects the ice shelf at the grounding zone. And then thinking about how surface waves of the ocean might affect ice, arbitrary vertical ice block. What we see is that wave force melting dampens with depth and doesn't impact freshwater, doesn't impact the seawater properties as much as we might have expected it to. We have a potential outlook for an analytically derived parameterization that consider both of these effects and could be potentially straightforward to put into models. To think about what's going on beyond these two projects and my general interest, I really like this figure because it nicely shows where my expertise has been so far in my PhD, focusing on this meters to kilometers scale around hours to days. I didn't chat about it today, but I also have a project thinking about subglacial discharge plumes. And really what I'm interested in is how do we connect these two scales, right? How do we leverage our knowledge from these high fidelity models that are over small regimes to improve the parameterizations that go into our ice shelf cavity-wide circulation models. So yeah, if anyone has any interests or chats about that, I would love to chat more. And with about 10 minutes left, I'll end it there. Thank you so much for listening and chatting, and I welcome any questions or thoughts.
Thank you. Any questions? Yes.
So at the end there, you mentioned that it's almost non-existent to have in situ observations. When you say almost, has it been done before? And if so, was it? I'm guessing it wasn't very successful, or?
Yeah. So one paper that comes to mind is there was a study done in 2016 in a Svalbard fjord where they set up a camera and looked at a marine terminating tidewater glacier terminus, and they saw it calving in this undercut being formed at the waterline. And the variable that they could relate it to the most was the wave height in the fjord. So like that's one example of an observation, but it doesn't necessarily get to like how are the waves eroding the ice, right? It just says that there might be a connection there. I'm sure Till can also speak to this. It's just incredibly difficult to get up to an iceberg or an ice terminus, right? It's nearly impossible without an autonomous vehicle. And once you're there, if you have money and the resources to get there, you have to be there for an extended period of time, right? To capture good data, and then also to be able to parse through what is driven by the waves, right? And what's driven by the ambient melting. So there's, a handful of records near marine tidewater glaciers or, instrumenting these ice with these observational things, but it's really only been in the last 5 years. And with that data, like, how do you piece apart these different ice loss mechanisms?
Thank you.
So for the wave-driven melting rate, it looks like you have a reduction in the upper portion due to a longer wavelength. That sounds like maybe you're assuming a constant wave state, like a certain amplitude for all the waves, and then you just vary the horizontal wavelength?
Yes.
Have you tried combinations of, like, for example, a higher sea state will correlate with a longer wavelength, and that the sea state amplitude maybe could boost that effect?
Yes, absolutely. So I haven't explicitly looked across both parameter regimes at the same time. But yes, you're right on the money that for that middle plot where I varied wavelength, I did keep the wave height constant. And this might show my personal shortcoming, but my understanding for ocean waves is that the wave height is going to be set by your fetch or your area that the wind's blown over versus your wave length is set by the wind strength, and I say that with a question mark because I'm not positive. So I think there's a general question there of how do we couple those two things together, and then also for assuming linear wave theory, is that a straightforward approach, or can we just say they're two separate things set by different phenomena? But yeah, you're right. If I was to include sea state variables similar to some of the other parameterizations, or combine the effects of wave height on that, then the waterline notch rate melt rate would be higher.
Evan.
This might be a dumb question because I'm not sure how complex your model is. I tried to follow along as best as I could. Do you have melting above the waterline? Because the way you stop at 0, is there anything above 0?
Right. So yeah, yes, that's a great question. I pretty much only think about this domain physically,
Okay.
At the waterline, so at theta. I think if I wanted to think about this upper portion of the domain, I might be asking more questions about ice dynamics themselves, of how tall does this notch have to be, or how
Yeah.
deep does it have to be for the ice to break off, right? But for now, we're just kind of thinking about, okay, you put fresh water in the ocean, what does that do? And so we don't really think about that upper part, but maybe a simple approach would be to just double the melt rate over that upper 5 meters or whatnot, because it should be somewhat symmetric.
You also, the picture you showed of the iceberg slowly rising over time, I wonder if you could get an extended notch if the ice is slowly rising over the course of days or weeks, and the notch is turning in, instead of one notch in one place, it's going to be getting wider over time.
Yeah, that's a great point. Something to think about.
Dan.
Could you just go forward a slide here? No, actually, I wanted to look at the melt rate there with the melt rate with the plume dynamics.
Oh, yeah, okay. So the dashed lines here.
Yeah. I mean, doesn't that suggest there wouldn't be a notch if the plume dynamics were important?
Yes, but your wave melt rate, which would be the solid line, is still stronger,
Oh.
right, within that upper 10 meters.
Those are separate.
Those are
Dash
separate,
line's
yeah.
Just the plume, or it's
Yeah.
just the plume induced.
So the solid line would be wave erosion only. The
Got
dashed
it.
line would be plume only.
Got it.
There could be a world where they're superimposed, right? Yeah, and then you would get that notch shape still.
So I think it's wonderful work, and it's so cool to see you all work on this. The thing that strikes me the most is that you essentially, the white, the original formulation is supposed to be the same as Big et al., right? In some ways, they're like, oh, white is too complicated. We're gonna replace it with something that's similar.
Yes.
But what you're showing really beautifully is that the answers are totally different, right?
Yeah, well, I think what's interesting, and I'd like to chat more because my impression is that White 1980 paper deduced this waterline notch rate that is
Yeah.
linear to temperature, and then it's been extrapolated to say that is wave erosion at all depth.
Right. And
Yeah, which is not true,
very
right?
strange.
And that
So
it's a
I
huge
have
difference.
one question, and then I'll let you go. We also have a faculty meeting. How do you determine how much the meltwater is mixed out in your model? What's your mixing coefficient there?
So it's not mixing. We have a your water comes in, and if there's a buoyant plume, then that's set by your density difference, right? And then the spread is equal to the flux of that plume into the surface box. And then we have our background velocity coming in that is replenishing that water, and that's just a value that we set.
So it's just a budget, essentially.
Yeah, yeah.
Okay.
So that's why I put in quotations ocean
Yeah.
model, because it's
Okay.
really just budgets of
Yeah.
water being moved around.
Great.
Yeah.
Well, thank you all for coming. I hope you learned something. And thank you, Madie.